Okay, so why don't we get started? We're going to continue talking about the economics of HIV/AIDS today. We really got started last time and discussed some of the different methodologies we can use to identify impacts short of a randomized experiment. We're going to continue that discussion and then talk about some decision-making frameworks. Since the first problem set was pushed back, I'm going to push problem set 2 to Tuesday. I'll be doing a week, and you guys will get solutions later on in that week, which is still a week before the midterm. So it should all work out. Any questions before I get started? Yeah. Oh. Okay. Not to me. Maybe the previous professor? Okay. Great. Okay, so let's get started. Last time we talked about how we would estimate the labor productivity impacts of HIV/AIDS related morbidity, in particular in this Fox et al. Study. And we started describing the data, which was collected on tea plantations in Kenya over 5 years. And so this data really is an application of the sorts of methods we started talking about last time, in particular the difference in difference approach. They had a sample of 271 workers, 54 of whom left work due to AIDS-related morbidity. Some of them ended up dying shortly afterwards. And they compare them to a group of 217 or whatever folks who did not become ill during the sample period. So that's the treatment here isn't like a medical treatment. It just means the affected group really are those who become ill with AIDS, and the control group are those who do not. So this is what the sample looks like. The n there means sample size in the first row. There's 54 cases, and so the cases here are what in our regression is t equals 1. T sub I1 equals 1. And the 217 in the comparison group are those that did not fall ill with AIDS during the study period. You can see that these two groups actually look broadly similar along a range of dimensions. The average age among the cases is 36 years of age, among the comparison is 37. So there's a little bit of a difference there. Although the p-value suggests that it's not a statistically significant difference. There is a pretty substantial difference in years of experience, 5 versus 6 years of experience. And there's also a difference in the gender of the cases in the comparison. So around 60% were male in the case group, around 70% were male in the comparison group. Okay, so going back to our estimation equations before, remember in reality there's a whole range of possible x's, meaning different characteristics of these individuals, some of which we might observe, some of which we can't observe. These are things we can observe. We can, if there is some sort of overall difference, say as a function of years of service, where you just say get better over time at your job, that can be controlled for here. Same thing if there are average differences by age, average differences by gender, those can be controlled for. Those aren't going to be the unobservables and observed characteristics, the omitted variables we're really concerned about because we can observe them. What we're concerned about is everything other than these characteristics. So these administrative records have this really great data on how many kilos of tea you pluck, and some basic demographics really, right? Gender, age, and experience. That isn't the full set of variables that might explain your productivity as a tea plucker. So there still are concerns about omitted variables that are plausible. What else do people see in this figure? Any other patterns or what sort of strikes you? Yeah. The p-value is the p-value on the test of the equality of the means across these two groups. So you can't reject the equality of the means on any of these dimensions at 95% confidence. But I would argue that in part is a result of the fact that they have a pretty small sample. So like a difference between 5 years and 6 years of experience, that seems substantial. It's a 20% difference in experience on average. But they're not quite powered up enough statistically to detect that as significant. So they're pretty big standard errors. And in general, like one thing that might jump out at you, we were just talking about the dewarding case before. Sure, dewarding had 75 schools, but 32,000 individuals. So here there's only 270 individuals. So it's a pretty small sample that way. Well, the sample size is going to be more of an issue in some ways for internal validity because it's going to tell us how precisely estimated we can estimate these treatment effects. The external validity question will be, are the workers on this plantation, say, similar to agricultural workers elsewhere? And there's a little discussion about these plantations, but they certainly don't present this kind of data or average characteristics for these workers versus, say, all ag workers in Kenya. That's what we have to know how representative these guys are for agricultural workers, say, in all Kenya or all of East Africa. So there isn't really extensive discussion that would shed light on external validity in this paper. It's a very kind of tight paper. There's a hand up the back, yeah.
With the different years of service,
yeah.
because the character has an additional year experience,
Yeah.
could you guess that the study will be focusing that will affect the age and productivity because of the differential?
You're saying if we didn't have that variable to control for, or they can control for this variable, right? So. Well, that's a variable that in theory would change over time. So there's a couple interesting ways that they use data that might be a little different to how I would do it. So first of all, here they're defining years of service as of the last day of service. It's not entirely transparent to me, at least in looking through how they use that variable throughout the analysis. In theory, that's a time-varying variable. Like every year you get one more year of service, right? So the diff and diff doesn't pose a problem in the sense that people are, you're getting time-specific data for everybody at every time point if you have that data. I mean, as a sort of aside, it's somewhat related to your question. It's more just a data construction question. Can you think of a reason why the cases would have less years of service on their last day of service than the controls? They stop working, right? So, again, what we really want to know is your years of service for like when we observed you in each point in time. And if sort of at each point in time, the treatments and controls or the cases and comparisons look pretty balanced on years of service, we're even less concerned. So there's almost like this mechanical reason why there would be that difference that, again, I would want a little more detailed discussion of how they use the covariates. They talk about a matching procedure that's used, for workers that are comparable to each of the cases on different characteristics. That isn't exactly how we would run a diff and diff in the regression that I basically gave you, on the slides before. Was there another hand up here? Okay, so what's really interesting about this data more than anything I thought is the descriptive evidence. So what they do is they define the kilograms of tea plucked per day for a worker, and they plot this out at intervals, at quarterly intervals, from 3 years before the death of the individual until their death. And again, they've matched the cases, the people that fall ill with AIDS, to comparison folks who look similar to them, sort of at the same points in time. So they're kind of comparing the comparison group to the cases when the case person, the treatment person, T equals 1, was 3 years, 3 years before their death, 2.5 years before their death, 2 years before their death, etc. So what are some patterns that immediately sort of jump out at you here? And looking at this, sort of the follow-on question, do we feel like diff and diff type assumptions seem more or less reasonable after seeing this time plot? That's going to be something very important for you to do if you're ever going to use these methods. You're going to first create data often that looks like this, and then you have to ask yourself, do I have more or less confidence in the diff and diff after seeing this plot? So what are some people's reactions to this figure? Yeah? Mm-hmm. Mm-hmm. More plausible. So that's a good point. So, if we go 2.5, 2.5, 3 years before, the sort of average kilos picked of the two groups is very similar to begin with, and they do look very parallel. Now, it's important to understand the progression of the disease at this time point when there were no antiretrovirals available, and obviously different people reacted differently to infection, and different people experienced different degrees of morbidity for different periods. But people would sometimes talk about there being a year to 2 years of morbidity before death, maybe a year to 18 months of morbidity before death. So in that case, the time pattern here actually looks pretty consistent with the way people talked about the progression of HIV/AIDS in a period before there were antiretrovirals, which is 2 years and before, maybe even a year and a half before the death. These two groups look actually pretty similar, and their trends are pretty similar. It doesn't look like the cases, the treatment group, are having any big drop-off in productivity before the time point where you'd expect morbidity to sort of kick in, maybe a year and a half or a year out. But then at that time point, you see a big drop in productivity for those who become ill, and there's a drop from about 40 kilos per day, which is about 90 pounds per day, that's a lot, down to maybe 33 kilos per day. Okay, so just in terms of our notation before, the controls are the T sub I1 equals 0, the cases are the T sub I1 equals 1. And the pre-period, if we wanted to group time periods together, this period over here would be the pre-period. This is like as early as they have data. And when we think about the progression of the disease, this is a time period before which there should be much AIDS-related morbidity. So this is the pre-AIDS morbidity period, and clearly right before death, or this is folks are basically leaving work at this point because they're too sick to work. That's the end point of our analysis, and that's definitely a point where there is AIDS-related morbidity. So that would be the post-period, the little t equals 1 period. So that, in our notation, that's how you could think of these different time points. And if we wanted to stick with 2 periods, we'd probably want to group all the observations before maybe here or here into a pre-period, and then group the others into the period where you're experiencing morbidity. And that'd be the way we would get 2 time periods. Any other thoughts or reactions to this figure? Yeah?
They don't give a huge amount of data points for the baseline. It would be because you can even see the people who eventually die, they're trending up at 3 years before death. So it'd be interesting to see what happened 4 or 5 years.
Yeah, it would be nice to have even more data. And they have a 5-year window, but I think they focus on 3 years because they don't have the full 5 years for everybody because people die and whatnot. I know the authors of this study, and we were at a conference when they were organizing basically the data collection. That was like maybe 2001. It was in 2001. And all the records at that time were paper records in this tea plantation. So they had teams of field workers going through and trying to photocopy them and enter them. And so, so they, even getting it for a few hundred workers, sort of on a daily basis, how many kilos you plucked, took them months of work. To the extent that now more organizations have digitized records already just for their own internal facility of using that data, it'd be much easier to pull long time periods of data. Any other thoughts or reactions? Yep. No, so they tried to match the controls to the treatments. And so they're kind of, for each case, they tried to match them with 3 controls or comparisons that were similar to them, worked the same parts of the plantation, et cetera. So they've matched them up, and this is really years before the death of what's called the case, the treatment person, the person who becomes ill with AIDS. And that's a very important question because there's no equivalent year of death for the control. So what years are you going to use? And that's one of the advantages of this matching approach. They say, we're going to define you based on your kind of baseline data, match you up, and then see how you evolve relative to the people that become ill. So there's a lot of intricacies with the data, and these are the kinds of questions that if you're going to use this kind of data, you have to think through very carefully. Because there's no one event time. It wasn't like everybody became ill in 1 month. So you can compare the cases and the controls to, in April of 2000 or something like that. People are getting sick all the time. So how you match up the cases and controls becomes very important. Yeah.
I was also going to speak on the death rate, because to me that it's not the becoming ill, it's fading into there's also the notion that you're going to die soon.
Yeah.
You just don't work as much as you could, like you're not reaching your potential labor productivity.
Potentially, yeah. Potentially, you just have so many other things to deal with at that point. So, that could certainly be part of it. And that would still be AIDS-related sort of loss of productivity because by necessity, if you're that ill, even if you could devote all your energy to working, you have so many other things to deal with. So, yeah. Yeah, right. We'll come back to that. That's right. The helper issue makes it a little harder to interpret these numbers as we'll come up with. But they were trying to earn as much money for their families or for their own health care before they were so ill that they couldn't work. Yeah. So the question was, can we still use a diff and diff approach if there isn't one period, calendar time of an event, but it's sort of staggered in this way? What are people's thoughts on that? Yeah. So with multiple time points, we're in sort of a panel data world. I mean, my view of this is they're doing the matching in part to deal with that issue. So once you match people based on the baseline data, then the event for that subgroup, the one sick person the 3 people are matched to, all relates to the event for the person who becomes ill. So that's kind of a clever way to get around this problem of there being these staggered events. You don't need to do it that way. You could use panel data with multiple time periods and just see the kind of decline in productivity individual by individual, where all the people who are not yet sick are the control group. So there's other ways to do it, which we could get into detail on, but their matching approach is like a very simple, transparent way of doing it that you could consider if you're using data of this kind. Okay, so I put these words up there, parallel trends. If you're going to use diff and diff data, or you're going to read a paper with diff and diff in any research seminar or any conferences, people are going to want to see evidence of parallel trends. And what parallel trends means is there's no evidence that these 2 groups had divergent patterns and a divergent sort of evolution of their productivity before the event here, sort of before becoming sick. I'm going to move this, it's sort of blocking the way. So what people often do to convince consumers of that research, to convince people at a conference or seminar, is show time plots like this. Try to show data before the event. So here people are starting to get sick a year and a half to 2 years out. That's kind of where the morbidity starts. So they want to go back as far as possible, sort of echoing the point before, and showing, look, these 2 groups had parallel trends beforehand. Now, one very important thing with the diff and diff, they don't need to have the exact same levels. They don't have to need to have the same values of their outcomes beforehand, because in the difference in difference approach, we're differencing out any fixed differences between the 2 groups. That's what the difference in difference is. It's saying, look, those that get sick and those that don't could have different productivity levels. because we're focusing on changes over time. What we're more concerned about is the cases were going way down even before they got sick. So we can't really attribute their decline in productivity to getting sick if even at 2, 3, 4 years beforehand, their productivity was declining very rapidly already. Then we would say, look, there's no parallel trends. There's evidence for pre-existing trends. And so you always, when you're using a difference in difference, want to get as much data as you can as far back in the past to test for pre-existing trends, pre-existing differential trends. And if you can show that they're parallel trends, and you can not only show it graphically, you can just test for it statistically. You can run a regression basically on those pre-time periods and check if the slopes are equal. So let me pause for a second. Any thoughts about that? Yeah. Yeah. Definitely. And what ends up happening very often in practice when you think of fitting data in this way is you can include a linear time trends. You can basically test whether the slopes are the same if you impose there's linearity, or you could include a second order term, time and time squared, which gets a quadratic form, et cetera, et cetera. Now, you can include a whole range of polynomials. You can include a fifth order polynomial if you have enough data, or seventh order polynomial. What people end up in some ways almost overfitting the data. If you put in enough polynomials into the data, you're very often the standard errors on those terms become very large, and you can say, well, I can't reject that these are the same. What people do in practice is they'll start with like a linear fit, and they'll test whether even a quadratic term is statistically significant. Are we even justified in going to these higher order polynomials first? If you are, then you might want to test these two terms, linear and quadratic, or even cubic, and see if you can reject the quality of those. But you have to be sure it's even justified to get into these more sophisticated functional forms by testing whether the second order, so the quadratic term is even statistically significant. So it's really more of an art than a science sometimes in the way it's practiced. And sometimes you have a lack of statistical significance because you're statistically underpowered, even though visually or intuitively it really looks like there are some differences emerging beforehand. And then that's sort of a gray area. You can't necessarily reject the claim or the hypothesis of parallel trends, but you may just be underpowered. Yeah.
I was wondering when the sample size is so different, the smaller sample is just going to be more.
Sure.
So how do you know? I mean, what is too small or what is too much information?
Yeah. So when you do standard power calculations, and there are formulas for doing this, and there's stata command for this, like the SAMPSI command in stata. You have to put in to that command not just the overall sample, but what proportion are in the different treatment groups, precisely because it has a huge effect on your statistical power. So given a certain sample, if you have a treatment and control group, you maximize power, you get the most precise estimates if you have equal sized groups. And that makes sense intuitively, because if you had one really tiny group that's incredibly noisy, comparing it to anything isn't that meaningful. So the standard power calculations require that information. It's like an important part of understanding how precise our estimates are going to be. Yeah. Yeah, we need to go to a regression. I'll show you the regression results in the next slide. This just alone visually, this doesn't have confidence intervals. This is just like really suggestive. And in some sense, this really does look like there are parallel trends. But that's something that we want to test. And what I'm going to show you is the levels. Actually, we can't reject that the levels are the same beforehand, but they're not explicitly testing actually for parallel trends in this paper. So there's sort of limits to how far they go with the analysis. Here, there's also different norms in different disciplines. And I think in a lot of the econ referee journals, they would absolutely demand that test. And in some other journals, they would demand other tests, which economics we wouldn't demand. So there's sort of like, there's only a certain amount of bandwidth you have for being rigorous, and different fields apply to different areas, something like that. I don't know. There was another hand up somewhere. Okay. So this is the sort of table with the regression results. And so what you can see here is 2.5 to 3 years out, the two groups look really similar. There's no statistically significant difference between the kilos they pluck per day. The p-values there are really large. And the differences even in sort of raw terms are very small, 1%, 4%, plus or minus. So they look very comparable actually in levels. But again, for difference in difference, we actually care more about the parallel trends. So that's the rub. Now because when we go right near termination, so the period just before termination or half a year before or even a year out, we're at more of a 19, 16, or 13% difference in productivity. So there's a pretty substantial difference in productivity. Now, what is the difference in difference estimate here? And how is that difference in difference estimate going to differ from just that final cross-sectional difference that I put in the red box? So think about kind of averaging the outcomes within the two red boxes and sort of in your head do algebra for what the difference in difference is, and then think about how that differs from the difference in difference on just this last cross-section. So what's the average of -4 and +1? Sort of like -1 and -2. And then the average for the latter period is 18 or something, or 17. Right? So the difference in difference is like -1 minus 17 or 18, right? About 18 percentage points. How does that differ from the straight up first difference? Or sorry, the straight up cross-sectional difference at the end. This is a very easy question. Meant to be. What's that? It's big? There's a big difference between the difference in difference and the straight cross-section? There's basically no difference because there's no difference at baseline. So the first difference doesn't bias anything because basically the difference is 0 at baseline. So this is actually a case where taking the double difference doesn't change inference. Maybe it increases the point estimate of the double difference by 1 percentage point. But it won't affect the significance level. Maybe it goes from a 17 point effect to an 18 point effect because they look so similar at baseline. In part, the way they construct the sample with these comparable pluckers 2 or 3 years before kind of buys them that comparability. So this is actually a case where the difference in difference isn't going to bias as much as it might in other settings. So this is just a way to walk through it. The pre-period is blocked up there. The post-period is at the bottom. And the first difference is, well, it depends on how you define. So their signs are the opposite of our signs in our regression.